So in section 5, we're going to work on solving quadratic equations by finding square roots. So the idea here is that if I can get my variable by itself on one side of the equation, either squared or in something that's being squared, then to solve I can take square roots of either side of the equation. So that's good for certain types of equations, particularly quadratic equations that don't have a middle term, but equally it's important for as we move forward and we start learning to complete the square, that will complete a square of a binomial on one side of the equation, and then we can take the square root of either side. So key vocabulary that we have here are square root, which you should already be familiar with. Radical, so it's one means of writing a square root as a type of notation. Radicand is a part of a radical. Rationalizing the denominator, we're not allowed to have irrational numbers in the denominators of fraction. So if we have that occur as we're taking square roots, we need to rationalize the denominator before we're done. And conjugates. I talked about conjugates in our section on the difference of two squares, the special pattern, and we're going to bring them back today, and they're a method of rationalizing certain types of denominators. So again, a type of problem where we might use this work deals with any time we're talking about an object falling. So on any planet, the height h in feet, now this would be height, of a falling object t seconds, so t is time, after it is dropped can be modeled by this equation. The current height is equal to the opposite of the gravity divided by 2 times the time squared plus h sub 0. So when you see h sub 0, that's the height at time 0, or the initial height. So for each planet or dwarf planet on the table, find the time it takes for a rock dropped from a height of 150 feet to hit the surface. So we have all these different gravities. Our initial height is going to be 150 feet on each one, and after we go through doing the skill practice here in the middle, then we'll go ahead and solve this problem toward the end of the lesson. To start, we want to go ahead and work on taking square roots. How do we simplify radicals? So for your vocabulary, this is a radical. The whole thing is a radical. There are other ways to write square roots besides radical form. Then we'll work on those later. But for now, that's what we're going to do, is write radicals. The item inside the radical, this 150, that's called the radicand. That was also part of your vocabulary. And when we're working with simplifying radicals, we're going to use a couple of different ideas. There's the product property. So what this says is that the square root of a times b is equal to the square root of a times the square root of b. And what that means for me as the student working on this is if I can factor the radicand, this 150, into different parts, if any of those parts are perfect squares, then I can simplify that part. And that's how I simplify the radical. So here is the example. We have the square root of 18. 18 can be factored as 9 times 2, so I can make the square root of 18 is equal to the square root of 9 times the square root of 2, and I did that because the square root of 9 is a perfect square. The square root of 9 is 3, so I simplify that part, and then I'm left with this other radical part that I can't simplify. So radicals are fully simplified, or let's say square roots for now, are fully simplified if I have factored out all the perfect squares and then simplified them. Okay, so whatever's left in here is the radicand can't have any factors that are perfect squares. Okay, and a very similar property is the quotient property. This was when I could factor it into things that are being multiplied times each other. Here, things that are being divided, I can actually separate the radical and separate the fraction and treat the numerator separately from the denominator. So here's our example, the square root of 2 over 25. I can leave the square root of 2, which can't be simplified, alone in the numerator, but the square root of 25 simplifies to be 5. Okay, so we're going to use these two properties and this idea that if I can separate out a perfect square, then I can find its square root and remove it from the radical. So when you take a look at 150, I know that 150 has 25 as a factor. So this is the square root of 25 times the square root of 6. Okay, now you might want to know, oh, how did I know that? Well, there are other ways to go about it, but I knew that 25 goes into 50 twice, and I know it goes into 100 4 times, so I knew it would go into these 6 times. If I had trouble with that, I could take the 150 and I could start doing a factor tree. So I know that this is 5 times 30, and 30 I know is 5 times 6, and 6 is 2 times 3. So typically you use this factor tree to get down to a prime factorization. I have nothing but prime numbers here at the bottom. But wherever I find two numbers that are the same, that's a perfect square. So I know that 5 times 5, or 25, is a factor. And then if you look at what's left, 2 times 3, that's where the 6 comes from. So you can do it by kind of looking at it and figuring it out. You could test with your calculator to check perfect squares to see if they are factors, or you could do this factor tree. All of those will work for you. Okay, so the square root of 25 is 5 times the square root of 6, and now it's completely simplified. Okay, sometimes we'll have items like this, where I'm going to want to go ahead and, I could go ahead and multiply these out now, but I highly recommend that you start by trying to simplify what you can. For instance, I know that 4 is a perfect square and that 4 is a factor of 24. So I know this is 5 times the square root of 4 times the square root of 6 times 3 times the square root of 10. Okay, square root of 4 is 2 times 5 is 10 root 6 times 3 root 10. Okay, now if I feel like I've gone as far as I can go, I can multiply the coefficients and also multiply the radicals. So you can see that square root of a times the square root of b would be the square root of a times b. So now I'm using this property going in the other direction. Before here I used it to split it apart going in this direction. And now I'm going to use this rule to put them back, these two radicals together. So 10 times 3 is 30. 6 times 10 is 60. Okay, so now I know that 4 is also a factor of 60. So I know this is 30 times the square root of 4 times the square root of 15. Okay, square root of 4 is 2 times 30 is 60 times the square root of 15, and now I'm fully simplified. Hey, if you wanted to see dealing with the 60 through the factor tree again, I know this is 2 times 30, I know this is 2 times 15, and I know that this is 3 times 5. I can see I have two 2's, so 2 times 2 is 4. That's a perfect square, and that's what I factor out. What remains? 3 times 5, which is the 15. Okay, so we want to go ahead and make sure that we never leave irrational numbers as the denominator of a fraction. So that's a violation of the rules of mathematics. There are things we can't have in the denominators of fraction, like 0 or irrational numbers. So if I look at this, first thing I want to do is I want to try to simplify it a little bit. So I know that 12 is 4 times 3. So this is the square root of 4 times the square root of 3. And square root of 4 is 2, and then the square root of 3 is 3. So first thing I did was I simplified it. And now the part I have to get rid of, the part that can't be in the denominator, is this part, the square root of 3. And up here there's a little guide for how do I get rid of it? What do I do? Well, if what I have is the square root of a number, I multiply it by itself, right? And these are other rules. If I have some number plus a square root, then I would multiply by the same number minus the same square root. Remember, these are conjugates. Conjugates create the difference of two squares, and that will allow me to get rid of the radical, as you'll see in future examples. And this is the same sort of idea about the conjugates. It's just this one had a minus, so this has a plus. This has a plus, so that has a minus. But I'm in this top situation. I just have the square root of 3. So I'm going to multiply the denominator by the square root of 3. And if I multiply the denominator by that number, I also have to multiply the numerator by that number. Okay, so this fraction that I use to transform another fraction or an expression has to equal 1. Right? So the denominator and the numerator have to be the same. So I'll end up with 7 root 3 over 2 times root 3 times root 3. Well, root 3 times root 3 is equal to 3. So when I square a radical, the result is the radicand. Again, to go back to your vocabulary words. So 7 root 3 over 6. This is fully simplified. Okay, so let's go on to another example. So now, right, I have this 1 minus root 3. If I look at this, there's nothing I can do to simplify it, so I'm going to move on to these steps. If I have a number minus a radical, what I have to multiply it by is the same number plus the same radical. So I'm going to multiply it by 1 plus root 3. And again, this fraction has to equal 1, so 1 plus root 3. As I go through this, in the numerator I'll have 2 times 1 plus root 3. And as I mentioned before, a minus b times a plus b equals a squared plus b, or a squared minus b squared. So if a is 1, I'll have 1 squared minus b is root 3 squared. Okay, continuing to simplify. If I distribute this, I'll have 2 plus 2 root 3 over 1 minus 3. So in reality, you can see that distributing here at this point didn't really help me simplify because my denominator's going to be negative 2. So I'm actually going to go back to this form. Distributing was not helpful at that point because what I want to do is I want to cancel common factors. So the negative, though, will stay. So I'll have the opposite of 1 plus root 3, which would also be equal to negative 1 minus root 3. So this is actually fully simplified. A lot of little steps, right? The step I did from here to here in the numerator was actually unproductive, right? So you might want to hold off distributing any multiplication until you've simplified. That's probably a good way to go. I was getting a little excited and moved forward too fast. Okay, so 3 examples really quick. I'm going to show how do you solve for a variable and also introduce this new idea. In these previous examples we had, the radical was already present in the problem. Okay? Now as we move forward, you'll see that the radical is not present in the problem. But in the course of solving, I am going to introduce the radical. When I do that, I also have to introduce plus and minus. Okay, the square root of a squared is a, and this will be plus or minus the square root of 50, but I can factor 25 out of that. 25 times 2. So a will be equal to plus or minus 5 root 2. Okay. So this plus or minus, that's a key element you're going to need to remember, and it happens when I introduce the radical. The radical wasn't already in the problem, but I added it in order to solve. That's when that comes into play. If you look at this problem, the first thing I want to do is I want to add the 6. My goal is again to get x squared by itself so I can take square roots. Negative 2 plus 6 is going to be 4. Now I'm going to multiply both sides of the equation by 25. That will get me x squared by itself. 4 times 25 is 100. And then I'm going to take the square root of either side, so x will be equal to plus or minus the square root of 100, which is equal to plus or minus 10. Okay, and one last example. This, by the way, is how things will look. This is an equation in vertex form. Right? Well, not quite, because this is not y equals, but this is similar to what you'll have in a completing the square problem. Right? Again, what I want to isolate, right? In the other problems, I isolated the variable squared. Here, the variable's in a binomial that's being squared. That's what I want to get by itself. So I add 18 to either side. I know I can't distribute the 7 because I would have to do exponent before multiplication. So instead, I'm going to divide both sides by 7. So I'll have x minus 4 squared is equal to 28 divided by 7, which is 4. And now I'll take the square root of either side. So x minus 4 would be equal to plus or minus the square root of 4. Square root of 4 is 2, so I have x minus 4 is equal to plus or minus 2. So x will be equal to, if I add 4 to either side, 4 plus or minus 2. So x would be equal to 4 plus 2, which would be 6, over 4 minus 2, which would be 2. Okay, so I end up with 2 solutions. All right, that's typical when you introduce the plus or minus. Okay, here's another example. For a science competition, students must design a container that prevents an egg from breaking when dropped from a height of 50 feet. How long does the container take to hit the ground? Well, I know I had that other formula, right? I had this minus g divided by 2t squared plus h sub 0. But for that matter, because we live on Earth, we're pretty used to the idea that height is equal to our gravity divided by 2. 32 feet per second divided by 2 becomes negative 16. T squared plus h sub 0. So this, for on Earth, this is the formula you can always use, that the height of a falling object is equal to the effect of gravity on its initial height. So gravity is negative 16t squared, and then plus the height you started at. In reality, this is actually a variation of a longer formula that deals with gravity in general. This is specifically for a falling object, but we also have this other formula. Height is equal to negative 16t squared plus the initial velocity of the object times time plus the initial height. So in this case, this formula actually works for everything, but it takes into account both the speed and the directionality of how the object is moving, because velocity can be positive or negative. If the item is being thrown up, it would be positive velocity. If it was being thrown down, it would be negative. In this case, because we're dropping the object, that means it's starting with an initial velocity of 0, so this middle term falls out. Just know that these two equations are the same equation. It's just that this one deals with an initial velocity of 0, or dropping an item, as opposed to throwing an item. Okay, so 50 feet above the ground. How long does it take the container to hit the ground? Okay, so I know that if it's hit the ground, its final height, the time I'm looking for it, it will have a height of 0. And its initial height is 50 feet. So if I add 16t squared to either side, and I divide by 16, then I can take the square root of either side. So t will be equal to plus or minus the square root of 50 divided by 16. Well, we've simplified 15 before, right? That becomes out to be 50 is 25 times 2. Square root of 25 is 5, still plus or minus, root 2 over the square root of 16, which is 4. Okay, now when we start thinking about this practically, time is equal to this positive number or the negative number. Is it possible, this again goes back to what I've told you when you're answering the question in a word problem. I've written the equation, I've accurately solved the equation, And now I have two possible answers. I need to logically think about which answer is correct. Is it possible for me to drop an egg from the top of a building and have it land in the past, right? That's what negative time would be. It would land before I dropped it. We know that's not possible, so the answer is 5 root 2 divided by 4. That's the correct answer, okay? Not negative 5 root 2 divided by 4. So even though I found this accurately, it's not accurate. So you may ask, well, what the heck is that negative number? Well, here's the building, and let's say here's the egg, right? What we're looking for is this part of the parabola where the egg is dropped and it falls to the ground. Here's the ground. The negative time is how long ago would I have to throw it to get up here to a zero motion point, right? At the very top, at the vertex, at its highest point, the egg would actually, for a brief, infinitesimal amount of time, have no velocity. It would stop there, it would cease going up, it would stop, and it would start going down. So this time here, right here is time 0. This time here, when I would have flung it from the ground, that's the negative 5 root 2 times 4. Okay, over here is the positive one, 5 root 2 times 4. This is the one I want. Okay, so be careful as you solve equations. Even though you've done the work correctly, you still have to think a little bit to answer the question. Okay, and now for our example about the different planets, and hopefully then we'll get a sense of what does this gravity power mean, practically speaking, around this. So what I think it's important for you to think about is which one of these is going to fall faster? The higher gravity number or the lower gravity number? And we're going to find out as we go ahead and do this. So I know that my height, right, we're talking about dropping it and having it land, right? So the final height is going to be 0. I know I'm going to have the opposite of 32 divided by 2t squared plus 150. Okay, now this is actually a case where I'm going to stop. I started right into doing Earth, and in reality, I don't really need to do Earth because I'm going to use this equation. I mean, I'm going to do Earth, but I'm going to use this equation 1, 2, 3, 4, 5 times. There is work that I can do to this equation before I start using it. So sometimes it's easier to start by just simplifying the equation. In each case, I'm dropping something and measuring how long it takes to get to the ground. So 0 is equal to the opposite of gravity divided by 2 times t squared plus the initial height, which is 150. So I know every time I'm going to add g divided by 2t squared to either side of the equation. So I could say the opposite of g divided by 2 times t squared equals 150. I'm sorry, not the opposite. I added it to either side. Okay, now all I have to do is plug gravity into this, and I've already simplified the equation. Okay, so this is going to be a little bit faster. So I can have 32 divided by 2t squared is equal to 150. That equals 16t squared is equal to 150. So t squared, actually I'm going to go ahead and go right to the solving. I know I'm going to divide by 16 and take the square root. I also know, as we learned in the previous example, that I can't drop something and have it land in the past, so I'm going to ignore the plus and minus. I know I only want the plus. So this will be the square root of 150 over 16. 150 is 6 times 25. We did that earlier, so it's going to be 5 root 6 over 4, and that's Earth. Okay, now if I do the same thing with Mars, you can see that I can put it in here and divide it by 2, or I can just skip right to the 12 divided by 2 is, right, 6t squared is equal to 150. Right, so this was Earth. This is Mars. So t will be equal to the square root of 150 divided by 6. Okay, so this is important because I'm going to have to rationalize this denominator. 150, you'll also notice, is going to simplify the same every time, isn't it? 5 root 6 over root 6. Oh, but I'm not going to have to rationalize. These cancel, so it just becomes 5 seconds. Okay, Jupiter. 76 divided by 2 is 38, so I'll have 38. T squared is equal to 150. So, sorry, T will be equal to the square root of 150 over 38. So that's, again, 5 root 6. Now 38, I'm trying to think of all the perfect squares that fit into 38. Half of 38 is 29. So if I were to do a factor tree, I'd have 2 times 29. 29's a prime number. So I don't have any perfect squares in 38. So I'm going to have to multiply this times root 38 over root 38. Okay, so my denominator will become 38. The 5 will ride along here, and I'm going to have, now, and I'm sorry, I'm starting to think about this going, let me examine this a little more because it'll help you understand that if I factor some of these things out, it'll actually help me do this. If I factor the 6, it's 5 root 2 times root 3. This is all going to be over 38, by the way, times square root of 38 is root 2 times root, not 29, sorry, 19. My mistake. I said 29 earlier, but it's 19. Okay, now you see this 2 and this 2. If I multiply square root of 2 times square root of 2, that's going to equal 2. So I can, by breaking it apart now, and finding perfect squares that are going to, right, I've got this prime, I have a prime factorization now of all the radicals. By spotting 2 radicals that are the same, I know that square root of 2 times square root of 2 is 2, times 5 is 10, times 3 times 19, so that's going to be 30 plus 27, that's root 57, all over 38. 10 is 2 times 5, and 38 is 2 times 19, so this becomes 5 root 57 over 19. Okay, so again, different ways to look at things by, instead of multiplying 6 times 38, by factoring it apart, I was able to find things to simplify, to make my life a little simpler. If we go to Saturn, I'm going to have 30t squared is equal to 150. So t will be equal to 150, the square root of 150 over 30. Well, 150, right, I can cancel the 10. 150 over 30 is going to equal 5. So it's just root 5. Okay, so I haven't been circling my answers. I should probably do that. Right, I stopped doing that work. This is Earth. Okay, and our final one would be Pluto. 2t squared equals 150. T is equal to the square root of 150 over 2. Right, that's going to be 5 root 6 over root 2. Now if I factor the root 6, so I could rationalize the denominator, multiply this by root 2 over root 2, or I could factor the root 6. That's 5 root 3 times root 2. The root 2's cancel, and I just get 5 root 3. Okay, so as you look at this, what you should get the sense of, if you actually calculate out these values, is that what happens is the higher the gravity, the less time it takes to fall. Okay? Mars took 5 seconds. Easy to compare Mars to Pluto, right? Mars is 5 seconds. Pluto is 5 seconds times root 3, so obviously that's more time than 5 seconds. Very easy to make that comparison. Okay, so really fast, you can see the key things that I did to make life easier is I went ahead and I simplified my formula first to make it very easy to plug in multiple items into this simplified formula. Okay, we went through a lot of examples of simplifying radicals, and we'll move on to 1.6.